Okay, this week's topic is chemical shift. This will be the only topic this week. Now, this is a very important topic because it has to do with a very common artifact called the chemical shift artifact. Usually occurs when you're imaging a muscle that may be surrounded by fat or other tissues that are surrounded by fat. So first, let's just, as a quick review, let's just look at the shape of water, the chemical structure of water, and the chemical structure of fat. This fat is, or this is really a fatty acid called butyric acid, which is found in butter. The point is just to show you, really quickly, the different chemical structure, because that leads into talking about proton shielding. So in water, there are, in every nucleus, you have electrons. So you have, what I'm showing here is these red circles. You have electron clouds, and those act to shield the nucleus from the magnetic field, which results in a slightly lower magnetic field than actually exists. So with fat, what happens is there's enough shielding that from all these different electron clouds, that this B effective is smaller enough than B0 so that you can see a difference in the resonance frequency between fat and water. So again, the point I'm making for the shielding is that protons in different microscopic environments resonate at slightly different frequencies. The microscopic environment of fat is different enough from water such that it has a relatively large frequency difference. Okay, some elements just don't have that large frequency difference, so we can't detect it. But with fat, it's big enough that we can detect. Usually we write the chemical shift as lowercase delta, so that for fat, for example, the resonance frequency would be this equation where delta is 3.35 ppm, or we would use 3.35 times 10 to the minus 6. So what is the reference then? How do we say what is zero chemical shift? Well, the spectroscopists have used historically something called tetramethylsilane, TMS, as their reference for 0 ppm, against which all other nuclei are referenced to. So for example, even water has a chemical shift of about 4.7 ppm relative to TMS. For fat, what we're going to use, we're not going to worry about TMS, we're really just worried about the chemical shift of fat relative to water. So we'll just say that fat, because this is true, but again, we don't have to reference fat to TMS, we can just reference fat to water. And fat, turns out, resonates at, most fats anyway, resonate at about 3.35 parts per million below water. And if we plot the MR signal intensity of an object as a function of the frequency, we have a spectrum. And this is how NMR spectroscopy, this is how the spectra are defined in NMR spectroscopy. So we can look at the spectrum, or the signal intensity of fat and water, using a spectrum to see this difference in frequency between fat and water, which is about 214 hertz. So here, this is what I'm showing. It's just it's not a real spectrum, I just drew it out, but this might be something that you may see. It'd be similar to this, as long as really the point being that the signal intensity from fat is 3.35 parts per million below water. Now it's important to use parts per million and really not hertz, okay, because the frequency difference is as a function of the magnetic field strength. So let's say, for example, you've been working on a 1.5 Tesla system, and then you start working on a 7 Tesla system. The frequency spread is no longer 214 hertz, it's actually 1050 hertz, which is a big difference, right? So so as long as you use 3.35 ppm, as long as you keep that in mind, you can't go wrong when you move from magnet to magnet, because all you need to do to figure out the frequency at 7 Tesla is to know that parts per million. So at 7T, you're at, let's see, what are you at? 300, about 300 megahertz at 7 Tesla. So 1 ppm at 300 megahertz is 300 hertz. Okay, so if we're at 3.35 ppm, whatever 3.35, again 3.35 times 300 hertz is about 1050 hertz. So as you increase, as your magnetic field strength increases, the difference in frequency increases between fat and water. So you get a larger chemical shift as the magnetic field increases. So I just want to mention a brief note here about the voxel intensity from fat and water. The spin density of water can be greater than that of fat in healthy tissue. However, the voxel signal from fat can be larger than that of water because the T1 relaxation of fat is shorter than the T1 of water. So if we look at a short T1 weighted scan, such as in a gradient echo scan, and the flip angle's 90 degrees, we're T1 weighted. The signal from water will be suppressed by TR divided by T1 fat. The signal from fat will be suppressed by TR divided by T1 fat. And the water and fat intensity ratio is reduced by T1 fat divided by T1 water. So you can see here, when TR is infinity, we have water to fat intensity. We have some ratio between water and fat, right? There's a difference here. But when we go to TR equals 40 milliseconds, we're now very much more T1 weighted. And since fat has a shorter T1 than water, the fat signal will be stronger at this TR. So this water to fat ratio has changed, or it's actually reduced with a shorter TR. Okay, so now let's get into the actual chemical shift artifact. So an important parameter that we have to talk about is something called bandwidth per pixel. So if we say we were going to acquire an image with a 256 by 256 matrix, and we're going to use a sampling time of 8 milliseconds, the necessary bandwidth is then 256 divided by 0.008 is 32 kilohertz. And this is the frequency range that we need to cover the length of the image in the x direction. So if we have 256 pixels in the x direction, and we have that 32 kilohertz bandwidth, then we can calculate a bandwidth per pixel as 32 kilohertz divided by 256, which is 125 hertz per pixel. So you see this frequency now is close to, at 1.5 Tesla, our chemical shift for fat. Okay, so you can start to get a feel for why this parameter is important. So let's assume we're imaging an object that contains water and is surrounded by fat. I want to talk about this. I want to begin to talk about this pixel shift of fat and water by talking about frequency encoding, because frequency encoding, the frequency encoding gradient, remember, it maps the precessional frequencies to spatial position. And if you remember, this is called Fourier encoding. And also the magnet is tuned to the center frequency of water, or the center frequency of the magnet is at the Lamour frequency of water, which is about 64 megahertz for a 1.5 T scanner. So because fat resonates at a slightly different frequency than water, fat will always be shifted Not always, but there will be some degree of shift in an image relative to the water in the direction of the frequency encoded direction. Now there actually will always be a shift, but whether or not you actually see the shift in the image is a different story, and that depends on the imaging parameters that you set up. And again, so like I said, it depends on the imaging parameters. So this frequency spread per voxel that we talked about in the last slide, this bandwidth per pixel, is very important, and it determines whether or not, it's one of the parameters that determines whether or not you actually see a physical manifestation of the fat shifting relative to water. So the chemical shift of fat, the actual physical shift in millimeters, can be given by this equation. And so from this you can easily deduce what happens. For example, if you decrease the magnetic field, you'll decrease the shift. If you decrease the bandwidth, you'll increase the shift. If you decrease the field of view, you'll decrease the shift. And if you decrease the number of pixels in the x direction, you'll decrease the shift. Probably a little bit more convenient way to do this, to look at this, is the number of pixels that you will shift, or n sub shift, equals the frequency difference between fat and water divided by your delta F pixel, which is bandwidth per pixel. So at 1.5 Tesla, the numerator here is 214 Hertz. And then the denominator is whatever you have set up as your bandwidth per pixel. So the physical distance that fat gets shifted is this number times the dimension of your pixel. So let's look at this now. What I've done here is I've shown an animation where I have three voxels that are next to each other. Okay, the voxel 2 and 3 have fat and water in them. Voxel 1 has nothing in it. Okay, just hypothetically. This row of X indicates the axis of the spin density. So here I'm showing spectrum of water, spectrum of fat, or a spectrum that shows water and fat. And because water in this case has a higher spin density, the signal is higher. Okay, but what's important here is to see where fat moves from one voxel to the next depending on the bandwidth per pixel. And remember, another point here is the chemical shift is really fat moving relative to water. Water does not move, again, because the magnet is tuned such that its frequency is the Lamore frequency of water. So because fat has a different resonant frequency than water, it will move in the presence of, it will appear to have moved in the image because of our gradient. So how much does it move? Well, if we set the bandwidth per pixel in this first case to a large enough value, the fat will appear correctly, or it will show up to be in the actual voxel where it's supposed to be. But if we reduce that bandwidth, let's say for 1.5 T, we've made the bandwidth per pixel equal to 214 Hertz, which is the same frequency difference between fat and water at that magnetic field strength. So in that case, what would happen is the fat from the third pixel moves to the second voxel. The fat from the second voxel moves into the first voxel. So now we have a pretty large, or we have a one voxel chemical shift. If we change that, if we reduce the bandwidth per pixel to 180 Hertz, we get an even larger chemical shift. So you can see if we keep reducing this, then fat 3 is going to move into voxel 1, fat 2 is going to move outside to another voxel. Okay, so this spatial misregistration becomes more severe. This spatial misregistration of fat becomes more severe as we lower the bandwidth per pixel. So what you see in the image then, you see bright bands and dark bands because of this shift. And what happens is, so it's important then to talk about the spin density alteration due to the chemical shift. So on the left, I just want to show you, I'm showing you 12 voxels, where the first 4 are water, the next 4 are fat, the next 4 are water. And on the bottom here, I'm showing the ideal image profile. So this is the signal intensity as we go across the voxels. Because I'm showing that water has a higher spin density, this is the particular signal intensity for these 4 voxels. Then when we make it to the fat location, signal intensity goes down a little bit, remains constant until then we hit water. So we go back up, over, and down. Now if fat is shifted over to the left by 3 pixels, you can see that we have a much different image profile or signal intensity per voxel. So again, the first voxel here remains the same, but the next voxel, the spin density has increased because what you're doing is you're adding spin density from water and fat in this voxel, and in that voxel. In the next voxel, the spin density is only due to fat, so it goes down to this value, which is the same as this level, right? But look what happens in the next voxel. There's no spin density, so there's no signal. So in this case, would be a dark. These voxels would be dark, and these voxels would be bright. As we move over, now we just go back to the same water that we had before. And this is manifest, what I'm showing is manifesting as bright bands towards the lower frequencies and dark bands towards the higher frequencies in the image. So this gray area is just the field of view of an image, where I'm showing that the whole gray area here is just fat, okay? And inside you have some water-bearing tissue, such as muscle. Now, if the frequency encoding gradient axis is the x-axis here, and the polarity of the gradient is as I've shown here, then what you would have, the chemical shift artifact would manifest itself depending again on what the bandwidth per pixel is. Let's just say the bandwidth per pixel was short enough so that we do have an artifact. Then you would see a bright band on this side of the image, because we're at frequencies that are lower than the Lamore frequency. On this side of the image, you would have a dark band because the frequencies here are greater than the Lamore frequency. Okay, so to summarize, remember the fat and water resonate at slightly different frequencies, and that's due to the electronic shielding in their molecules. So we use the term chemical shift as just a brief term to describe this difference in resonant frequency between fat and water. So chemical shift of fat is 3.35. I think Shemi mentions 3.5, but I've used this number. I got this number from a different source that I think is a little bit more accurate. Again, the chemical shift artifact manifests itself in the frequency encoding direction. So let me go back. Now, in this case, if we had done frequency encoding along the y-axis, then the bright band would be at the top or bottom, depending upon the polarity of the gradient in the y-axis. Okay, so now let's think about the x-axis. If we change the polarity of gx, the bright band would move to this side and the dark band would move to this side. Okay, so I meant to mention that before, but since I reminded myself during the summary, so So to decrease the chemical shift artifact, you could go to a weaker magnet, but practically speaking, you're not going to change magnets. You're going to either increase the readout bandwidth or you're going to decrease the field of view. Okay, so please read as soon as you can the journal article number 6, because I felt that gives really good additional background on this topic. The author also shows some clinical applications of this, so it's not the artifact is an artifact. You usually don't want it, but there is some more information in the paper that talks about how you can use to your advantage this difference in frequency in resonance frequency between fat and water, and it's very important. So please email me any questions you might have on the lecture notes or the paper. Thank you.